Hello, everyone. We are starting lecture number 11 today. There is a second lecture about profunctors, and if we'll be done with them quicker, we'll go to the next topic, weighted limits and colimits. But for now, let's continue with our profunctors. So last time, we defined profunctor to be a functor between a bifunctor whose first variable is contravariant and second one is covariant, and values lie in a cosmos V. For set profunctors, I'm now referring to the first column right now on the screen. We found that there is so-called span and cospan representations. What do I mean by that? That for every profunctor, we can define comma category A, comma B over profunctor P, and we can define co-comma category A, co-comma B over P. Well, who's our category of our comma category consists of? It consists of arrows, formal arrows from A to B. That formal arrows I will denote by dashed arrows, X, and pairs of objects, one from category A and other from category B, and pro-commutative diagrams made morphisms in that category. About co-comma category, we understood that it has objects. So objects are objects of A coproduct with objects of B, category B, and morphisms from A to B, from X to Y, are given in 4 different ways. First way as morphisms in A, if both objects are in A. Next one, morphisms in category B. Third way, okay, I don't have space there, so I need to write separately. Third way as values of our profunctor, P from X to Y. And the last one is an empty set if X belongs to B, Y belongs to A. So this was about co-comma category. Also, morphisms from category A to category B are called heteromorphisms. So homomorphisms are morphisms from the same inside the same category, and heteromorphisms are morphisms from one category to another one. We have defined 4 functors: domain, codomain, bottom, and top. So domain and codomain are usual functors for comma categories which extract first or second component. And for co-comma category, we have embedding as category A as itself and category B as itself inside co-comma category. Okay, but how does this can be related back to our profunctor? It can be related in the following way, that every profunctor from A to B can be decomposed through its comma category or co-comma category. Also, comma category was called graph of P, and co-comma category as co-graph of P, which makes sense if you will write instead of your functor some simpler functors that you are used to do, and it will precisely look as you think about graph or co-graph in usual mathematical sense. And these decompositions are written here. Okay, this was what was the last time, and even before that, we have defined a composition. Composition of 2 profunctors P and Q are given by at pair AC is given by coend of the following bifunctor. This bifunctor has fixed AC, and we are changing B in covariant and in contravariant position here. So it's well-defined functor from B op cross B to set or to cosmos V, and from of that functor we are taking coend. Okay, and this gives us the composition. And also we have identity. Identity is given by the identity profunctor, home profunctor. So taking home as identity and composing our given profunctor with homes on either side gives us counada lemma, as a covariant counada or contravariant counada lemma. And vice versa, counada lemma proves this fact. So either way you talk about it, you can get it. So the first thing what we will do today is that we are going to define to look at the internal structure of category of profunctors. Category of profunctors has a very interesting thing inside it, especially when V is a cosmos. It has right can extensions and can lifts. Before, we were talking about can extensions in the following way, that if you have category A, functor going to category E, this was functor F, and we had functor K going to category B, then we could find a right can extension, or right can extensions were can extensions that were going from the composition to given functor. Right can, sorry, I am constantly saying can extensions. Professor Marcinkowski gave me today second notice, and I guess the third one will be the last. So can extensions. So from composition of can extension and extender towards the functor. That's can extension. So what is can lifting? If you have a functor, again, from A to category E, and you are trying to lift it against a certain function from category D to category E. So here's our F. Here, let's call J. We are making this lifting. Since will be talking only about right, so it's a rift of functor F against functor J, and we have a morphism. Sorry, I have a natural transformation again from a composition to F. This is called rift. I would say that people also usually talk about can extensions, but not can liftings, since in general in categories can liftings do not exist, neither left, neither right. They exist in some rather I would say not artificial, but partial situations, and you can't expect them to happen very frequently. Well, of course, you can take that in certain way, embed your picture of right can extension inside the other category, where you will reverse all your functors arrows and preserve two-cell natural transformation given by natural transformation, and then you will have somewhere can lifting, or vice versa. Having can lifting, you will embed it somewhere which has can extensions, and then you will get this lifting. But do not hope to do this on in every single category. However, in category of V profunctors, we have this fantastic thing that for any two profunctors that either are going from one category, either are landing in the same category, we have can extensions and can liftings, both are right. How they are given. So if we have this picture that I'm right now moving my pointer at, then in a left part we have can right can extension, and in the right part of it we have right can lifting. I precisely draw this diagram as we do this for our projective and injective modules, for you to also remind and recognize yourself that extension and lifting from module theory, or in general from algebra, is just a partial case of can extensions or can liftings. In that case, usually you are doing with some precise extension. However, in general, it is known, I haven't proved this, that even if your functor has extension, it's not necessarily can extension. So can extension a little differs, but it's everything factors through it. Usual extension just extends your functor, but not necessarily every other extension or almost extension will factor through it. The formulas are given for right can lifting and right can extension by the formula that I'm trying to underline right now. So to get your right can extension, you are taking natural transformation between common variables of two functors. Who is a common variable of P and R is A. So you are taking natural transformations on a contravariant component. And if you are taking two functors that land in the same category as category C, then you are looking at natural transformations on covariant components. Values of contravariant components or covariant components in either case that are left, there we plug in coordinates or pairs of objects for our profunctors that we want to compute at. Either of can lifts extensions can be also given by the coend. How does this happen? Is we have a theorem that natural transformations between two functors is given by an end. So that I gave by ends here in the formula, let's say 1, here in the formula, say 2. Well, and now I want to introduce a certain notation. So when I will be talking about can extension of P along R, both are profunctors, I will write P right division by R. And if I'm talking about right can lifting of K against S, I will be writing K left divided by S. So you have fractions actually. Why they are fractions, you will see in a second. So I'm going right now. Can I move screen? I, as usual, will give you notes later. So why do we have this this notation? Because we can talk about adjunction. So part 2 is adjunction. So given 3 profunctors, P, Q, and R, and not necessarily commuting triangle, I emphasize on this. So it's just 3 profunctors. We can write down the following the following triple adjunction. As usual in this adjunction, you can see one covariant and one right contravariant adjunction. So we see here that if we have product or composition of profunctors and natural transformation in the third one, we can extract or divide by either of arguments in the composition on either side. In other words, I would say that my composition, so P composition is left adjoint to right can extension, and my another composition Q is right contravariantly adjoint to rift Q, and here is a blank. Using the division notation, you can see what I do. Also, I'm sorry. Also, I want to emphasize on the following thing, that I am taking product of composition of profunctors diagrammatically. So in order they appear in a diagram. Also, sometimes you can write Q composition, Q composition P, and this is completely the same as P diamond Q. So P diamond Q is a notation in a diagrammatic order, Q composition P in a usual composition order. And even if you here use Q composition P, then division on the right will give you this thing, division on the left will give you that thing. That's very natural to see. Okay. So that's about the adjunction. How can you prove this adjunction? You can prove it so when you define the formulas as above, you can prove this adjunction by just quant calculus. So jungling with ends for ends, with tensoring, with internal homes, you will get all this triple adjunction. And converse, given such a junction, so that something is adjoined into that, you will derive that it should look exactly that way. So our formulas for right can extensions and can liftings are precisely the consequences of quant calculus that we developed before, and nothing else. So the conclusion is the following: that composition of profunctors is divisible on both sides. Why this is important, we will see in a very little bit today. Okay. Also, I wanted to mention that division on the left or on the right by identity profunctors gives us contravariant unit and covariant unit elements. Just plug in your identity profunctors in the formulas of RAN and Rift above, and you'll see that. Okay, this was about this internal structure. However, to go even a little deeper, and this will be super helpful later today, we need to talk about actions of profunctors on functors. So what do I mean by action? As you remember from general algebraic courses, that if we have a group, sometimes we can find a set on which group acts. It means that for every element of a group and element of a set is defined there. Some composition or action of group element on the set element gives another set element. Such that this composition is generalized, satisfies generalized associativity and unitility. So identity element acts as identity function, and composition acts the same way as if we act first by one factor, then by another factor. Okay, so what is a right action? Suppose we are given two objects. One is a profunctor P, and another is functor F. Then we can define F tensor P. In every single book, it is written P tensor F. So we are tensoring on the other side. However, for a purpose of that, it is right action, as you can derive that it's a right action. I want to write it on the other side. So I'm not writing P tensor F, but F tensor P. So what is F tensor P? I know how to compose two profunctors, but how to compose profunctor and functor, in general, I have no idea what and how to do. But I see that I have a common variable. If my profunctor and functor are going from one category, then it is contravariant for profunctor and it is covariant for a functor. Then I form bifunctor, which has one variable covariant, one contravariant, but from the same category. And then I am taking the equivalent of it. Another variable that's left here, it will be a variable for to plug in for the result. By the way, I need to emphasize that f of a is an object of category E. So we have tensor product, let's say it this way, of object of category E with potential object of category V. So our self-enriched category. This we can't usually multiply. So if our category E was here V, self-enriched one, then that's okay. We know how to do that. However, in general, we do not have right to do it. So to do this, I need to give you or remind, if I was giving it before, cannot remember, what is V-tensored category. So V-tensored category, it's a category where you can act by your coefficients in a specific way. What I'm talking right now about. So a category, enriched category is called V-tensored if there exists a bifunctor which is denoted as, again, as tensor. I know there are too many tensors. You will ask me, so why everywhere tensor? Well, maybe one day I will give a little order in all this math, because everywhere is the same symbol. I know it's heavily overloaded, so it depends on which context we use it. However, it is some sense that it's everywhere the same. So if there is a bifunctor, which we call tensor, which pairs together coefficients or objects from Cosmos V and objects from category C, and gives us again objects of category C, such that it is left adjoint to covariant home. So covariant home, when we fix one first covariant variable, and contravariant variable is fixed, so we change only covariant variable. If it has left adjoint, then this left adjoint is called tensor. Okay. When and how we can see this? I immediately can give you example. If you will take ab, then here you will take lambda mod. You can make tensoring to lambda mod in a way that abelian group A tensor over Z and with module M. Okay, so you can tensor every module with an abelian group, because every module is a abelian group itself. And this will be adjoint. So this blank tensor Z M will be adjoint to home lambda M comma blank. You can check this yourself. This is usual tensor home adjunction. Okay. So when we know how to, let's say, tensor or multiply objects of our category by coefficients or by sets or by abelian groups, whatever we have, then we can define tensor product of functor and a profunctor. And this is called right. In this will be right action. Why? Because you can check by hand that f tensor p tensor q is isomorphic to f tensor p composition q, and this formula is written precisely in a way how it appears. If you will be writing tensoring with p on the other side, then first you will be tensoring with again with p, but then with q, so you will get a little mess. And tensoring with trivial profunctor, of course, gives you the same functor. I don't think that you will be surprised that I will call it Coyoneda. So I will call it then, as it was at Can extensions lecture, generalized Coyoneda. This is generalized, of course, Coyoneda. Okay, left action. For left action, I am taking profunctor and then taking functor, and now I want to take a cotensor. So what is a cotensor? Cotensor is an operation which is right contravariantly adjoint to contravariant home. Yes, again, you see today that I have one covariant adjunction and one right contravariant adjunction. In the next lecture, this all will make sense, and we'll see that it's everywhere, or almost everywhere this thing happens. So this operation, we can think about this as some sort of division by sets or by abelian groups or whatever, is given by this pitchfork sign, and it's called cotensor. Okay, you will ask me what is a cotensor in previous example. I will give you immediately an answer that what do we say? A cotensor M will be given as home over Z from A to M. So here it is. And of course, then you can see that home over Z from blank to M is right contravariantly adjoint to home over lambda from blank to M. So this is what about this is all about our adjunction. Okay, here's A, not lambda. So when our category is cotensored, we can perform such operation. So between objects of category E and coefficients, and coefficients in category V, and taking end it gives us cotangent. This operation is left action that can be checked directly, and in some sense you can think about this as a product of profunctor by general functor, and it's given by cotangent. But nevertheless, we have action of profunctors on category of functors when it satisfies, when the target category in a functor category satisfies tangent or cotangent property. Are there any questions to this moment? Okay, if there are no questions, then we will move forward. Yes, you can also ask me about what that. This is, if you think about modules, this will give you a restriction and extension of scalars. Restriction, co-restriction, and extension of scalars. So when you have a bimodule, or you have a change of rings, then your one of rings becomes a bimodule over original ring and over itself using homomorphism of rings, and then this right action will give you extension of scalars and so on. And all these adjunctions that you usually have, either in representation theory and homological algebra, will where you use tensoring or homing from a bimodule certain to your module, you will have precisely this action of profunctors in your functors. Again, I want to remind that modules are functors, covariant for left and contravariant for right, and profunctors are bimodules. So RS bimodule is a profunctor from one object category R to one object category S. For details, I'm referring you to our last lecture. Fine. If there are no questions, then we are moving forward. We already spent, I think, as usual, too much time on the previous topic. So what will be the following topic? Let's name it a little surprisingly for you. Let's name it barrels. Let's name it barrels, and also so this will be okay. Let's just be barrels. The next one will be fine. So let's give a definition. So let C be a category. This all for non-enriched setting right now. So let C be a category. A functor from C to category of ordinal 1. I will remind you this is a category of just two objects and one non-trivial arrow. A functor B is called a barrel. So morphism. Morphism of barrels is given by a functor between source categories. So here C1, here is category C2, here is your category 1, here is your barrel B1, here is your barrel B2, and here's functor F. So this is a morphism of barrels. Okay, then definition. What even? Let's not be definition. Remark. So, comma category. Cat, comma 1 is a category of barrels. Of course, of small barrels, because we have domains small, but I'm not usually thinking too much about this size issues. So we have a category of barrels. So it's a comma category. Here is a fixed category, here category changes. And morphisms of domains are morphism of barrels. Okay, then another remark is gives us the following. So when you have your category C and you have your arrow from 0 to 1, then you split your category such that this part is going to 0 and that part is going to 1. So this is your barrel B. And you have that this is pre-image of 0 and this is pre-image of 1. There are interesting properties that by -1 of 0 has arrows. No, let's write in the following. If arrow lands in by -1 0, then it starts. Then it starts there. So if a certain arrow finishes here in this category, then it starts also here, because otherwise it will start in by -1 of 1, and all objects have their images, either 0, either 1, and we have the violation. There is only one non-trivial arrow from 0 to 1. By -1, so pre-image of 1 has similar property. So if arrow starts in by -1 of 1, then it lands there. The first property is called sieve, and second one is called co-sieve. So if you have sieve, its complement is co-sieve. So complement of sieve equals co-sieve, and complement of co-sieve is sieve. It's the first thing. And second thing, there are so if S is sieve, then we can define a unique barrel. No, we can uniquely define a barrel if S is barrel, let's say B, such that B -1 of 0 is S. If S is co-sieve, then similar statement with by -1 of 1 equals S. So sieves, co-sieves, and functors from the category to an interval are in bijection. So we have sieves in category C are in bijection with co-sieves in C are in bijections with barrels. Okay. So now let's talk a little about what what is an internal structure, what is a relation of category of barrels with other categories. So when we have category of barrels, it's a comma category, but it's specific comma category, as barrels, as I said before, define sieves and co-sieves, and sieves and co-sieves are both categories. So how we define a sieve? So we are taking our function c from 0, or from functor b from c to 1. We are taking inclusion of a single object with single arrow in category of our interval, and then we are taking 2 back. So here is our b per image of 0. So here is a pullback. In a similar way, we can obtain our co-sieve, which is per image of 1. Every object here is a category. So here, by minus first of 0, by minus first of 1 are categories. So we have defined a function. Unfortunately, I do not have many names in my head, so I call it again bottom and top. Maybe it's worse to call it sieve and co-sieve, but it's quite long names. And barrels, if you imagine barrel full of water, alcohol, or whatever you want, it has usually bottom and top. So bottom and top of barrel are our maps, which gives us sieve and co-sieve, gives us pair of categories. Cat cross cat. There is another inverse operation that will be left adjoined to this one. This will be operation of coproduct. So you are taking 2 categories. You are mapping these 2 categories to trivial category of one object, 0. And these 2 objects, 0 and 0. So I will say that here is just 1 0, here is another 0 that can be viewed as 1, can be embedded in such category 1. So this functor will be left adjoined to our bottom top functor. In other way that you can imagine barrel. So barrel is, here is your b minus 1 of 0, and it has some arrows, maybe not arrows, we'll call them later staves, 2 by minus first of 1. So this is a barrel. Here, your first operation gives you trivial barrel. So this will be your barrel, which has this and this. So it's by minus 1 of 0 and by minus 1 of 1. This is trivial barrel. Okay. But there is another also trivial barrel that we need to think about. It's a barrel where every point or every object in sieve is connected with every object in co-sieve. So here, we will have by minus 1 of 0, by minus 1 first of 1. It's also trivial barrel. So how we will get this one? This is by minus first of 0, join by minus 1 of 1. Have we defined join ever? Join of categories? Do you remember? Please tell me. If we haven't, then I will do this. Okay, so I missed this in comma categories. So I will define what is a join. And here we'll have just by minus 1 of 0, coproduct by minus 1 of 1. So these are extreme cases. This you can think about anti-discrete category, or how you call it, indiscrete category. So in this indiscrete case, and here you'll say about discrete, or vice versa. I don't know where to put them. So here we also have another functor, which will be a right adjoint to bottom top, and it will be given as join of two categories. Join is functorial. I will define what is a join. This goes to 0, 0, and this is isomorphic to an interval. Okay, now let's say a few words about join. So what is a join? So join of categories. So if you have definition A and B categories, then define A join B a category. Whose set of objects A is given by objects of A join union objects of B. The first thing. And second thing is that for so morphisms of A, B are given by morphisms of A, disjoint union, morphisms of B, disjoint union with exactly one morphism from every A belonging to A to every B that belongs to B. So if I will write down, this is my A, this is my B, two objects, then join will be category that has arrows in A and B, but it will have also all arrows between A and B. So this is A join B. Remark that if we define profunctor P A op cross B to set by the rules that pair AB goes to a singleton, then co-comma category of this profunctor P is isomorphic to join. If you define profunctor P from A op cross B to set, here will be A, here will be B. It goes to an empty set. Then your co-comma category will be isomorphic just to coproduct of categories. Coproduct of categories, as I told you in the beginning, put on the left one category, put on the right another category, and they have no intersection, but together they still have, still form a category. That's just trivial examples of our joins. Okay, then what would I say? Yeah, since we have a unique, exactly one morphism from A, from every A to every B, then composition of morphism from. So if you have from A prime to A and from A to B exists unique, and this is alpha, then this is also unique, and this triangle necessary commute. So you can think about join or these morphisms between different parts of join as bottleneck. So every time you're going from A to B, there is only one way to go from A to B. But from every, you can go to it. And the composition is well defined. This is similar if from B to B double prime. Here will be beta. Here also will be unique. Map and this triangle commutes. So composition B with unique one will be good, well defined, and this will be exactly that map that you expect it to be. Okay, this was about the join. So when we are joining, so example, when we take 0, join 0, what do? We are taking object here. Let us call it 1. 0, let's here object 1. They have identity loops on them. And we are joining them exactly with one arrow from 0 to 1. So here is 0, join 0. It's a new 0. And this is isomorphic to an interval. Also, m join n. It is m plus n plus 1, as I remember. So just for you to remember. So what we got, so conclusion. Conclusion is the following, that category of barrels with category of categories form such triple of have such triple of functors that the middle one has both left and right. In science, you will see that it's called a recollement, or in English, people pronounce it recolement. So it's a triple of functors that are adjoined to each other, as I remember. And such triples of functors quite often occur in math. But it's just one of their examples of recollement. Okay, then now, after saying this, I will push further to a bit surprising results. What they will be? They will be about category of barrels and category of profunctors. I haven't talked any time right now about any profunctor, but still we are in lecture about profunctors. So something goes wrong. You think with me? No, that's not the case. I want to define a new category which differs from category of profunctors that was defined before. So category dist. Why? Because sometimes profunctors are called are called distributors. Yes, profunctors called distributors, and identity profunctor home in fact works as Dirac delta. So if you know a little generalized functions, convolution and so on, you can find connections between profunctors and theory of distribution. So if function is generalized by distribution or generalized function, then functor is generalized by distributor. So I would call this category dist. However, it still consists of profunctors. So what are objects? So dist from A to B is a category whose objects are profunctors P from A to B and a morphism from profunctor P from A to B to profunctor C, D. Sorry, not enriched, nothing is enriched here. And morphism between two profunctor is given by a triple F alpha G, where F is a functor from A to C, G is a functor from B to D, and alpha is a natural transformation, but not arbitrary, but specific one. So what should I do? I am taking my profunctor Q here from C to D, okay? Then I have a functor from A to C. Then I can make a profunctor, which will be called C super F. It is a co-representable profunctor. And I can make a profunctor from D to B, which is D G below. It is representable profunctor. And here I also have my profunctor P. So natural transformation alpha is given from a P to composition of Q with these two guys. So alpha goes from P to the composition C super F, diamond Q, diamond D, G. Or if you want, it is Q, F, G. Okay, so you have something similar to category of twisted arrows. If you remember what that. So twisted arrow category is where you are working not as in comma category, where you have just diagram squares, but one arrow is going opposite way. So this is a category of distributors from A to B. Then you have a structure of by category on distributors. So it is by category. Wait a second. Mm, okay, this is a by category. So it has objects. So it's what small categories. Then profunctors are arrows, and F, alpha, G are two cells. Okay, then you have you have category of small categories. It's a two category. Category of small categories is again two category, and their product is two categories. So this is two category. Then for every for every A and B, one second. I probably missed some information when I was thinking about this. Okay, let's do it the following way. Let's clear this. Yes, it's true, but I don't need to think about it this way. So my apologies. So this objects are all profunctors. So it doesn't matter where they start and end. The first thing and second morphisms F, alpha, G are arrows. So your objects are profunctors. So profunctors are not arrows, they're objects, but they do not have fixed end, ending or beginning. And then we have we have an equivalent. So theorem. There is an equivalence between category of distributors and category of barrels. So to one side is going functor collage, and to another one is going functor state. How do we define them? So collage of profunctor P from A to B is given by a map from A comma B over P to 1. So objects from A objects are going to 0, B objects are going to 1. So I have reminded in the beginning what is a comma category. So you are separately taking objects of A, separate taking objects of B, and then glue them together by profunctor P. So now you smash together all arrows between A and B into one arrow. And all objects in A are going to 0, and all objects in B are going to 1. This is functor collage. Functor state. we need to take a barrel and make a distributor from it or profunctor from it. So state from barrel B, so we have C, B to 1 is given by a profunctor B minus 1, 0 to B minus 1, 1. So here is our bottom, here is our top of barrel, and between top and bottom, so if we have top and bottom, there are staves. So every stave will be a value of the given profunctor that we define. And here it is defined by just home. So homes from the bottom to the top are profunctors. So not general, I would say home. So home is going from C to C. It's our home profunctor. But now I need to include my pi minus 1 of 0 here, and here include B by minus 1 of 1 include. Okay, so this is they form an equivalent. So collage of state equals 1 and state or isomorphic to 1, and state of collage is also isomorphic to 1. Are there any questions? I mean, surprise, surprise, but barrels were very close to profunctors, or category of profunctors, in a very, very strange way. Okay, and the next topic, I think the last one for today, or pre-last one, we'll see how time allows us, will be called co-continuous functors between co-complete categories. So let's make certain notation. So comp is a category of all small co-complete categories and co-continuous functors between them. We also can write co-cont from A to B as a category of all co-continuous functors between co-complete A and B. There is a very powerful theorem that tells us. So you can find it in the book of Kashivara Shapira. About categories and sheaves, which tells us so that for continuous functors from category of pre-sheaves on category A to arbitrary category B is equivalent to a functor category from A to B. Isn't that beautiful? So this equivalence is, I would say, not immediate. You need to play a little with that. It involves also can extensions. We haven't been talking something around it to a little get closer to it. But this is very, very important fact. Why it is important? If we, so corollary, if we consider for continuous functors from, let's say here, B op set to A op set, then it will be equivalent to category functors from B to pre-sheaf category and category A. But the latter one is equivalent to category functors from A to B, from A op cross B to set, and the last one is defined to be a profunctor category from A to B. So co-continuous functors between pre-sheaf categories are isomorphic to profunctor category from A to B. Such surprising result. So profunctor category can be also viewed as co-continuous functors between pre-sheaf categories, but in opposite order. I will comment on that and say here again, Yoneda, sorry, not CON extensions are involved, and so-called free co-completion. If the time will allow us next time, maybe I will mention what are CON factorizations. So factorization of CON left and right CON extensions. It precisely goes through category of pre-sheaves. Okay. Then the next thing, what I want to say here will be the following. That I can define two functors I want to define two functors. One will be from profunctor category from A to B to the category of co-continuous functors between A and B. No, I don't want to do this way. This will be correct, but so I'm taking category of all profunctors and going to category of co-complete categories. Yes, here it is. How do I work? I'm taking category A. It's an object of category of profunctors, arrow subprofunctors, and it goes to the following profunctor category. So category of profunctors from a trivial category to category A. I want to remind you that trivial category has one object and one arrow on it. So it's a very, very long category, the smallest one, besides empty one. And that from A to B profunctor category is functor category A op cross B to set. So when we put profunctors from I to A, it is the same as I op cross A to set. It is the same as, so I op is the same as I, and multiplying with a trivial one object category gives us nothing. So it will be A to set. Similarly, if we have A to trivial category, this is A op cross trivial to set, which is precisely pre-shift category. Okay. Now, I want to remind you that limits are in functor categories computed pointwise. So if E is co-complete, then functor category from DD is so. So either complete or co-complete. E gives us that functor categories values in E has the same property. Set is by complete category. So from this follows that from A to set and functors from A op to set are both by complete. In particular, they're co-complete. Now returning to our function. From A, I am going to profunctor category from trivial to A, which is isomorphic to category of so-called co-preshifts. So preshifts are from A op to set and co-preshifts from A to set. And if you have a profunctor from A to B, say P, this will go to composition with P, and this is the same as tensoring our functor with P, if you will unravel the definition. This functor is usually denoted as lower shrink, or as I already told you, it's precisely trivial, comma blank. So it's a representable. Function from prof to comp in this way. Of course, representable should be not from prof but to cat, but it factors through co-complete categories. Fine. Then the last question is why this functor is co-complete, co-continuous, sorry. Why it is co-continuous? Because it is co-continuous as it has right adjoint. And right adjoint is given by left action. So this one was right action. And its adjoint is left action of profunctors on functor category. So it is co-continuous that was desired. Both categories of copper shifts on category A and on category B are co-complete, and functor between them is co-continuous. Similarly to this, I am defining functor, which will be denoted as upper string, and which is precisely contravariant functor, represented by representable contravariant functor represented by trivial category, which is taking prof op to co-complete categories. So every profunctor P op is going to composition with composition on the left, and this is precisely again tensor and USP. But now tensor and USP for op on the opposite, in the opposite way. Now I want to state the general statement about these functors that we just defined. So theorem, it's named by, so it's proved by Morita, Watts, Laware, and Binabu. It tells us that lower and upper string are equivalences of categories. So our category of co-complete categories is equivalent to category of profunctors in such specific way. Or you can consider our profunctors as maps between co-continuous functors between co-complete categories. And now one additional statement. So if A to B, I call it phi, is a functor, then representable profunctor, composition is a representable profunctor from such profunctor category 2. The composition with co-representative profunctor gives us a junction, and this can be unraveled as the adjunction between perceived categories given by composition with a functor and left-hand extension along this functor. But I need to emphasize not functor, but its opposite. So these are all isomorphic. So this is what we have about profunctors. Now I want briefly to summarize, and we will end. So summary. So first, profunctors are generalized relations distributions by modules, matrices. Second, every profunctor is a composition of co-representable with representable or respectively co-representable profunctors. So we have this decomposition that I started with it and was the topic of the last time. Third, composition of profunctors, factors through radiation category. 4. So this was all from previous lecture. Now from today's lecture. Vprof is biclosed, symmetric, monoidal, bicategory. This means that this has, let's say, composition has 2 adjoins, so run and rift. 5 is dist equivalent to category of barrels. 6 that profunctors from A to B are equivalent to co-continuous functors from perceived categories. Bop set to a op set. And 7 profunctors define the following equivalences between co-complete categories and themselves. So they can be considered something similar to that. So this is very, very briefly what we obtained up to now. So what will be next time? So next time will be first weighted co-limits. So they are generalization of limits and co-limits in enriched category theory, and not only in enriched, also in usual one. Second of all, full quant calculus, since we had a few rules, but with weighted limits and co-limits, we'll have all rules. And third, tensor home cotensor situation. So tensor home cotensor situations are similar to what we had today. So examples are V tensored plus V cotensored categories. This is all for today that I had for you. Thank you very much for your attention. I hope you a little understood and a little enjoyed. Thank you, Rahul. This topic about profunctors, I found it very promising, and that you can find much more applications and usage of it. I haven't covered even a little part of what exists in literature. There are many more connections. Also, I want to add that profunctors nowadays play a significant role in computer science, not theoretical, but practical one. They are used in so-called theory of Tambera modules, and Tambera modules model so-called optics, and optics is one of the modern, I would say, fashionable topics in programming. What is optics and how to use it, it's very different story. And it's now was before optics, now it gets as profunctor optics, so profunctorial view on it. And there are some, I would say, similarities and analogs of theory of Cauchy completions, co-completions, and flat modules with theory of profunctors and profunctorial completions. There are so-called equipments of pro-arrows in bicategories, and many more topics, Fourier transforms, and all this is related and based on profunctors. So who wants to learn more? You can always ask me or look through the literature. And now I'm welcoming you to ask any questions if you have. And thank you for your attention again.
Thanks, Alex.
Thank you, Sean. Thank you, everyone. So I'm then stopping the record.